calculate the lighting load for a 120-volt circuit, you can use a straightforward formula. The lighting load in watts is equal to the number of fixtures multiplied by the wattage per fixture. The first step is to count the number of lighting fixtures connected to the circuit. Secondly, determine the wattage of each individual fixture. This information is usually found on the fixture's label or in the manufacturer's specifications. Thirdly, multiply the total number of fixtures by the wattage of each fixture. For example, if you have 10 lighting fixtures and each fixture is rated at 60 watts, the calculation would be as follows. Lighting load in watts equals 10 fixtures multiplied by 60 watts per fixture, which equals 600 watts. It's important to note that this formula only accounts for the lighting fixtures themselves and does not include any additional loads such as switches, dimmers, or transformers. To calculate the total load on a circuit, you need to consider these extra components as well. Always ensure that the calculated lighting load remains within the capacity of the circuit breaker or fuse protecting the circuit. Refer to the circuit's electrical specifications to determine the maximum allowable load. A general recommendation is to keep the lighting load below 80% of the circuit's total capacity. This safety margin provides allowance for future expansion or additional loads on the circuit. Staying within the 80% limit helps prevent overloading the circuit, which could lead to trip breakers or, in more severe cases, electrical hazards. Always consult local electrical codes and regulations for specific requirements and guidelines related to electrical installations and load calculations. When determining the appropriate circuit breaker size for a lighting circuit, several factors must be considered. Firstly, the total calculated load of the lighting fixtures and any additional components like dimmers or switches. Secondly, the National Electrical Code, or NEC standards. The NEC provides guidelines for overcurrent protection to ensure safe operation of electrical circuits. Thirdly, the continuous load. The NEC generally requires that circuit breakers be rated at not less than 125% of the continuous load. This is outlined in NEC section 210.20. This means that if a lighting load is expected to operate continuously for 3 hours or more, the circuit breaker should be sized accordingly to handle the increased demand. To determine the minimum circuit breaker size, start by calculating the total lighting load in amps. This can be done using the formula amps equals watts divided by volts. In this case, we are dealing with a 120-volt circuit. Once the total load in amps is calculated, multiply the value by 1.25 to account for the continuous load requirement. The result is the minimum ampacity rating required for the circuit breaker. Choose a standard circuit breaker size that is equal to or greater than the calculated minimum ampacity. Standard circuit breaker sizes typically include 15 amps, 20 amps, 30 amps, and so on. It's important to select the appropriate circuit breaker size to provide adequate protection against overloads and short circuits, while also avoiding nuisance tripping. If the calculated minimum ampacity falls between two standard circuit breaker sizes, it is generally recommended to choose the next larger size. However, it is crucial to ensure that the conductors, or wires, used in the circuit are also rated to handle the chosen circuit breaker's ampacity. The conductors must have an ampacity equal to or greater than the circuit breaker's rating to prevent overheating and potential fire hazards. In addition to the continuous load requirement, other factors may influence the selection of the circuit breaker size. These include voltage drop, conductor rating due to ambient temperature or conduit fill, and any specific requirements outlined in the NEC or local electrical codes. Always consult with a qualified electrician or electrical engineer to ensure that the circuit breaker size is properly selected for the specific application and in compliance with all applicable codes and regulations. Proper circuit breaker sizing is essential for electrical safety and the reliable operation of lighting circuits. By following these guidelines and considering all relevant factors, you can help prevent overloads, short circuits, and other electrical hazards. When installing or modifying electrical circuits, always prioritize safety and adhere to established electrical codes and regulations. If you're unsure about any aspect of electrical work, it's best to consult with a qualified professional to ensure the job is done safely and correctly. Let's consider a more detailed example to illustrate how to calculate the appropriate circuit breaker size for a lighting circuit. Suppose we have a lighting circuit in a room that includes the following fixtures: 6 recessed lights, each with a wattage of 75 watts, 1 ceiling fan with integrated lighting, drawing 1 amp at 120 volts for the fan motor and 60 watts for the light, and 1 dimmer switch controlling the recessed lights. Step 1. Calculate the total wattage of the recessed lights. Total wattage of recessed lights equals 6 fixtures multiplied by 75 watts per fixture, which equals 450 watts. Step 2. Calculate the wattage of the ceiling fan light. The ceiling fan light wattage is already given as 60 watts. Step 3. Calculate the wattage of the ceiling fan motor. To convert amps to watts, we use the formula watts equals volts multiplied by amps. Therefore, the ceiling fan motor wattage equals 120 volts multiplied by 1 amp, which equals 120 watts. Step 4. Calculate the total lighting load. Total lighting load equals recessed light wattage plus ceiling fan light wattage plus ceiling fan motor wattage. Total lighting load equals 450 watts plus 60 watts plus 120 watts, which equals 630 watts. Step 5. Calculate the total current in amps. To find the total current, we use the formula amps equals watts divided by volts. Total current equals 630 watts divided by 120 volts, which equals 5.25 amps. Step 6. Account for the continuous load. Assuming the lighting load is expected to operate continuously for 3 hours or more, we need to account for the continuous load requirement. Multiply the total current by 1.25 amps. Continuous load current equals 5.25 amps multiplied by 1.25, which equals 6.5625 amps. Step 7. Select the appropriate circuit breaker size. Choose a standard circuit breaker size that is equal to or greater than the calculated continuous load current. In this case, the next standard circuit breaker size is 15 amps. Step 8. Verify conductor ampacity. Ensure that the conductors, or wires, used in the circuit are rated to handle the 15 amp circuit breaker. Refer to the NEC tables for conductor ampacity ratings based on wire size and insulation type. If the conductors are not rated for 15 amps, you will need to use larger conductors or reduce the circuit breaker size accordingly. Step 9. Consider other factors. Check for any additional factors that may affect the circuit breaker size, such as voltage drop or conductor dirting due to ambient temperature or conduit fill. Adjust the circuit breaker size as necessary to account for these factors. In this example, we determined that a 15 amp circuit breaker would be appropriate for the lighting circuit, assuming the conductors are rated to handle 15 amps and there are no other significant factors affecting the circuit breaker size. Always consult with a qualified electrician or electrical engineer to verify the circuit breaker size and ensure compliance with all applicable codes and regulations. Remember that this is just an example, and the specific calculations and considerations may vary depending on the specific lighting load and electrical installation. Always prioritize safety and consult with a professional when working with electrical circuits. Understanding the ampacity of wires is crucial for ensuring the safety and reliability of electrical circuits. Ampacity refers to the maximum amount of electrical current, measured in amps, that a conductor or wire can carry continuously without exceeding its temperature rating. Exceeding the ampacity of a wire can lead to overheating, insulation damage, and potentially fire hazards. The ampacity of a wire depends on several factors, including wire size, material, insulation type, and installation conditions. Larger wires have a greater cross-sectional area and can therefore carry more current than smaller wires. Copper wires generally have higher ampacity ratings than aluminum wires of the same size. The type of insulation used in the wire also affects its ampacity. Different insulation materials have different temperature ratings, which determine how much heat the wire can withstand before the insulation starts to degrade. Common insulation types include THHN, THWN, and XHHW. The installation conditions of the wire can also impact its ampacity. Wires installed in conduit or enclosed spaces may have lower ampacity ratings than wires installed in open air due to reduced heat dissipation. The National Electrical Code, or NEC, provides tables that list the ampacity ratings for various wire sizes and insulation types under different installation conditions. These tables are essential for determining the appropriate wire size for a given electrical circuit. When selecting wires for an electrical circuit, it's important to choose wires with an ampacity rating that is sufficient to handle the expected load. The load is the amount of current that the circuit is expected to carry. It's also important to consider any damping factors that may apply. Damping factors are adjustments to the ampacity rating to account for factors such as high ambient temperature, multiple conductors in a conduit, or voltage drop. To determine the appropriate wire size for a circuit, start by calculating the total load in amps. This can be done using the formula amps equals watts divided by volts. Next, consult the NEC tables to find the ampacity rating for the wire size and insulation type that you are considering. Make sure to account for any damping factors that may apply. Choose a wire size with an ampacity rating that is equal to or greater than the calculated load, after accounting for damping factors. It's always a good idea to choose a wire size that is slightly larger than the minimum required size to provide a safety margin and allow for future expansion. For example, suppose you have a 120-volt circuit that is expected to carry a load of 15 amps. You are considering using THHN wire, which has an ampacity rating of 20 amps for 14 AWG wire and 25 amps for 12 AWG wire. If there are no damping factors to consider, you could use either 14 AWG or 12 AWG wire. However, it would be better to use 12 AWG wire, as it provides a safety margin and allows for future expansion. If there were damping factors to consider, such as high ambient temperature, you might need to use an even larger wire size. It's important to note that using undersized wires can be dangerous and can lead to overheating, insulation damage, and potentially fire hazards. Always consult with a qualified electrician or electrical engineer to ensure that the wires are properly sized for the electrical circuit. When working with electrical circuits, always prioritize safety and follow all applicable codes and regulations. Proper wire sizing is essential for the safe and reliable operation of electrical systems. Let's delve into the concept of voltage drop and its impact on electrical circuits, particularly lighting circuits. Voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to the conductor's resistance to the flow of electrical current. As electricity travels through a wire, some of the electrical energy is lost as heat due to the wire's resistance. This loss of energy results in a reduction in voltage at the end of the conductor compared to the source voltage. Voltage drop is an important consideration in electrical circuit design because excessive voltage drop can lead to several problems, including reduced lighting brightness, inefficient operation of electrical equipment, and potential damage to electrical components. In lighting circuits, voltage drop can cause lights to appear dimmer than they should be, which can affect the overall illumination level and visual comfort in a space. Electrical equipment, such as motors and appliances, may not operate efficiently or may even fail to start if the voltage is too low due to voltage drop. Excessive voltage drop can also cause overheating of electrical components, which can shorten their lifespan and increase the risk of electrical hazards. The amount of voltage drop in a circuit depends on several factors, including the length of the conductor, the current flowing through the conductor's resistance, and the voltage of the source. Longer conductors, higher currents, and higher resistance all contribute to greater voltage drop. To minimize voltage drop in electrical circuits, it's important to use appropriately sized conductors, minimize circuit lengths, and reduce the current flowing through the conductors. Larger conductors have lower resistance and therefore result in less voltage drop. Shortening circuit lengths reduces the overall resistance of the circuit and minimizes voltage drop. Reducing the current flowing through the conductors can also help reduce voltage drop. This can be achieved by using more efficient electrical equipment or by distributing the load across multiple circuits. The National Electrical Code, or NEC, provides guidelines for voltage drop in electrical circuits. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual loads, such as lighting fixtures and receptacles. Feeders are the circuits that supply power from the service entrance to the branch circuits. To calculate voltage drop in a circuit, you can use the following formula: voltage drop equals current multiplied by resistance. The current is the amount of electrical current flowing through the conductor, measured in amps. The resistance is the resistance of the conductor, measured in ohms. The resistance of a conductor depends on its length, cross-sectional area, and material. You can find the resistance of various conductors in the NEC tables. Once you have calculated the voltage drop, you can compare it to the NEC guidelines to determine if it is within acceptable limits. If the voltage drop exceeds the NEC guidelines, you will need to take steps to reduce it, such as using larger conductors or shortening the circuit length. In addition to the voltage drop formula, there are also voltage drop calculators available online that can help you calculate voltage drop in electrical circuits. These calculators typically require you to input the circuit parameters, such as the conductor length, current, and wire size, and then they will calculate the voltage drop for you. When designing electrical circuits, it's important to consider voltage drop and take steps to minimize it to ensure the safe and efficient operation of electrical equipment. By using appropriately sized conductors, minimizing circuit lengths, and reducing the current flowing through the conductors, you can help reduce voltage drop and improve the performance of electrical circuits. Always consult with a qualified electrician or electrical engineer to ensure that electrical circuits are designed and installed in accordance with all applicable codes and regulations.